So now we've got another little technical remark, remark 2, continuity on non-open intervals. So the way that continuity was defined earlier, essentially we have a function that is continuous on some open set, which means some sort of set. We can think of an open interval. That's an open interval. So in this case, we've got these two little open circles here. And that's how continuity is defined for us, because we can think about at a point, you can surround that point with a little open interval, and then inside this open interval, you can do a left hand and a right hand limit. Even if we take a point really close to the end here, the fact that this is an open circle at the end point specifically means that you can't actually get to that point. So if we do an example here more concretely, maybe instead of a to b, maybe we say that this is from -3 to 4. Okay, so here's some function f, and f on this open interval -3 to 4. Well, we can't actually plug in 4 into this function. It's only defined for real numbers strictly greater than 3 and strictly less than 4. But here's the interesting thing. We can get as close to this real number 4 as we like. We can do 3.9, 3.99, 3.999, 9999, so on and so forth. We can type in any number that we want to and make it as close to 4 as possible. So because of that, we can think of, even if we get really close, we could, right here at 3.999, actually surround it with a little open interval, which means we could investigate and actually explicitly check both the left and the right hand limit. And that's how we define continuity, was a function is continuous at a point if the left and right hand limits exist and agree at that point. So if we have a function defined on an interval that is possibly not open. So what are examples of non-open intervals? Well, we could, if we wanted to, actually close this off. And in which case, we are able to actually plug in 4 into the function, and that means the function is defined there. In which case, because we now can plug in 4, if we try to surround 4 with an open interval, it's not going to make sense for our function, because while all of these values to the left of 4 and including 4 are part of the domain of f, nothing to the right of 4 is defined. So while it would be possible to check a left-hand limit, so we could definitely do the limit as x goes to 4 from the left of f, but it would not be possible to do a right-hand limit. That's not possible. So based on our definition of continuity, we couldn't say that f is continuous on this interval unless we have this additional remark. So here's the convention. The convention is that a function f, if it is defined on an interval such as a closed interval a to b or a half open interval, maybe it's closed on the left and open on the right, or maybe it is, maybe this is closed on the right instead of the left. So no matter what kind of interval you're using, any of these non-open intervals, instead of requiring an open interval on every single point, we can just relax our conditions on these included endpoints, and we'll only require that the function be left continuous here. Or if we had it closed on the left endpoint, then we only require it be right continuous at the endpoint. So this is just a more relaxed, these are more relaxed conditions at the included endpoints. More of a technical, definitely more of a technical point here, but it is essentially is what allows us to say a function is continuous on any of these intervals, not just the one we began using to define continuity.